Hello everyone. In this example, we're going to look at a two-factor ANOVA using jamovi. Right? So in this example, we're looking at two separate independent variables. We're looking at drug, and it's going to be drug A or B, and gender as male or female. And we're looking at the differential impact of these two drugs on men and women in terms of their memory scores. Okay? So the first thing we're going to do is label our variables, because right now, like drug A and B are just labeled 1 and 2. So we want to change that to A and B. So I'm going to double click on drug AB, and then I'm going to change the 1 to an A and the 2 to a B. Right? And then after that, I'm going to click the up arrow to hide that menu. And now you can see my data file is labeled with A's and B's rather than 1s and 2s. Now I'm going to do the same thing with gender. And the data are scored so that 1 is equal to male and 2 is equal to female. So I'm going to change 1 and 2 to male and female, and now that way my output will be labeled with males and female rather than 1s and 2s. Right. This step isn't absolutely required, but it's really helpful to have your data with verbal labels rather than a bunch of 1s and 2s. Okay, so we're going to do an ANOVA, clicking on the ANOVA menu, and click on ANOVA under that ANOVA menu. And then we're going to move our dependent variable, which is memory score, into the dependent variable box. And then we have two separate independent variables. We have gender and drug. So we have two variables, gender and drug, and we're looking at their impact on this dependent variable, which is memory scores. So we have our overall ANOVA summary table here. I'm going to add to it omega squared. You could also add partial eta squared if you're interested in those effect sizes as well. Okay. So you can see here that we have our output for gender on the first line. We have the results for the drug main effect on the second line. And then we have the gender by drug interaction on the third line. So there are three overall effects we're testing for here. We're going to start by looking at the gender by drug interaction. So if we look at the gender by drug interaction, we can see that we have an F with 15.98 degrees of freedom and a p-value of 0.0001. So that tells us that it looks like we have an interaction in our data. So we're going to take a look at that interaction. We're going to start by clicking on Estimated Marginal Means, and we're going to look at the Marginal Means table. Right. So look at the Marginal Means tables. We're going to need to look at gender by drug. Okay. So it's looking gender by drug. I'm putting both of those into the terms, and it's showing me a graph of gender by drug, and then also a table of the gender by drug. So if we start by looking for males, right, we can see that for men, their memory scores were higher with drug A than with drug B. For women, their memory scores were higher with drug B than with drug A. So the definition of an interaction is that the effect of one independent variable depends on what level of the other independent variable you're talking about. So in this case, the effect of drug A versus B depends on whether or not you're male or female. Right? We have an interaction with a very low p-value here. That means that this difference we're observing is not likely to be due to sampling error. Okay, now to follow up on an interaction, what you do is compute simple effects tests. Now in jamovi, to get simple effects test, you click on the post hoc test box. And we are going to look at the gender by drug simple effects. We are using no correction here and selecting Cohen's d with a 95% confidence interval. Okay, so there are two different ways you can look at simple effects. We could look at the effect of drug A versus B for males and then for females, or we could compare males to females at drug A and at drug B. In this example, we're asking you to look for males, is there a difference between drug A and drug B? And then for females, is there a difference between drug A and drug B? And then to describe those differences. So what we're looking at here are for males, drug A and drug B is the first row in this output. So what this shows us is that for males, there's a difference between drug AB of 2.987. That's the difference between drugs A and B. Right? So that is the difference between drugs A and B here. Drug A was higher than B. You can look at the table down here as well and see it's for men, it's 19.72 for drug A and 16.73 for drug B. That difference is moderate to large in size. Cohen's d is 0.69 with a low p-value here of 0.004. So that is our simple effect, showing that for men, the difference is unlikely to be due to sampling error and that scores were higher in drug A than with drug B. Now for women, we're going to go down to the very last line. For females, drug A and females, drug B. Here we have a difference of negative 2.84. And that's showing us here that drug B was higher than drug A by 2.84 points. Our p is 0.0066, which is a very low p-value, suggesting that that difference is unlikely to be due to sampling error. And our Cohen's d there is negative 0.66, which is again a moderate to large effect, but it's in the opposite direction as the effect for men. So we clearly have an interaction here in that our p-value for the overall Anova was low. And in terms of describing that interaction, we're saying for males, they had higher scores with drug A than drug B, and that difference was unlikely to be due to sampling error. And for females, the difference that they're looking at was that scores were higher with drug B than drug A, and that difference was also unlikely to be due to sampling error. You'll notice here that when you ask for effect sizes, you can also get confidence intervals around those effect sizes as well. And when you're interpreting those, remember that if the effect size, the larger or the wider the confidence interval or is around that effect size, the less precise our estimate is of the population parameter. And the way to get narrower confidence intervals is to have a bigger sample size. Okay, so next we're going to look at the main effect of gender. So when we look at the main effect of gender, I'm interpreting this first line here. And you can see that our F value is 0.66 with a P of 0.42 and a omega squared of basically 0, which shows us that the difference between males and females overall, ignoring which drug they took, was likely to be due to sampling error. Now if you want to see which means you're comparing, you can go down to estimated marginal means and click on add new term here, and we're going to just look at gender. So now look at just gender. You can see that males look like they have slightly higher memory scores than females. Their score is 18.23, females is 17.63. But when we look at our p-value up here for the gender main effect, we can see that that p-value of 0.42 means that the observed difference for them is likely to be due to sampling error. Okay? And it's a very small effect, if any at all. Now we can do the same thing to look at the effect of drug. So when we look at the effect of drug, we can see that the F is 0.0098 with a P of 0.92, which means that on average there's no difference between drug A and drug B. We can look at the marginal means by clicking on add new term and then moving drug A and B over. And here, when I scroll down and look at drug A and drug B, I can see that they're basically equivalent. The average score for drug A was 17.966. For drug B, it was 17.894. Okay? So there's really no difference between drug A and drug B. But notice how uninteresting those main effects are. We're saying that there's no difference between males and females on their memory test scores, and also our main effect of drug shows that there's no difference between the two groups in their memory score performance. But that clearly doesn't tell the whole story. The really interesting result here comes from the interaction, where we have this interaction that's unlikely to be due to sampling error, and we find very different effects. For males, they did much better with drug A. Females did much better with drug B. Right? And so that is the interaction that's really important there in terms of the interpretation. And usually when you're doing two-factor designs, interactions are the reason you're doing them. You want to know whether or not the effect of one independent variable is different for different groups or a different independent variable. All right, so that is what you need to do the activity and answer questions about this. Note that when you're reporting the numbers in APA style, they are coming from this table up here. Mean square residual is the mean square error. And when you report the degrees of freedom for each effect is always going to be 1 in the numerator, or the first number, and then the second number will be 1 to 36, which is the degrees of freedom residual. Other than that, all of the results you report for each effect go on this first line here. Or I'm sorry, not on the first line, but are associated with the line for each effect. Okay. When you report the post hoc test, or really the simple effects is what they are, you're reporting the data from the top row for males and the data from the bottom row for females. At least in my output. If you put your data in a different order, you're going to have a slightly different looking set of post hoc tests, but the numbers will all match up. Okay. One last bit of information you need is you will need to get standard deviations for each of your groups. So you'll note here that in jamovi it gives you the standard error rather than the standard deviation for each group. So in order to get the standard deviations, you click on the exploration menu and click on descriptives. You move your dependent variable, memory score, into the variables box, and then you split the file by drug A and gender. Okay. And that will give us the means, median, and as well as the standard deviation within each group. Okay. All right, so that is all you need to run these analyses in jamovi. Okay, and that is all you need in order to run these analyses in jamovi. Okay, good luck.